All right, so we're starting section 9.1 here, quadratic graphs and their properties. We're going to go back to graphing functions. These are just going to be of this shape. Instead of being linear, these are often referred to as non-linear. Okay, we've talked about some that were non-linear already, like exponentials. This is another type of non-linear function. It's called a quadratic function. Quadratic function can be written in the form of y equals ax squared plus bx plus c. Okay, and when it's written this way, that's called standard form. Okay, in the last chapter we worked on factoring that. So let's say we had like y equals x squared plus 5x plus 6. We learned last chapter that we could rewrite that as x plus 2 times x plus 3. This is standard form, and this is factored form. Okay, and there's actually another version of this that we can write that you'll learn about down the road a little bit, called vertex form. But this is the format that we're going to start with here in this section. Says reminder, obviously this is a function. Okay, so we got to remember what a function was. A function is a particular relationship. Okay, so it's an x comma y relation, or a set of x comma y relations, in which each x value has one and only one y value. So it's a set of ordered pairs that every x value that you see has one and only one y value. So if I say everybody look at an x value of 1, they know that it has a y value of 1. And that's the only y value that will ever go with this one. If I look at an x value of 2, say everybody look at 2, then everybody will know that 4 is the only y value that goes with an x of 2. Okay? So if you remember what that meant, that means that this thing, if I make a vertical line through here, make this vertical line and then grab it and start sliding it, okay, left to right, my vertical line will only ever intersect that graph one time. And what that means is that for that x value that the vertical line is passing through, we're getting only one y value to be paired with it. So that's what it means to be a function. Okay. So a lot of times what they do with this type of stuff, since we know it is going to be a function, instead of using y like I do here, where it says y equals x squared, they will say f of x equals x squared instead. Okay, that there and that there are the same thing. Okay, we even get to the point when we talk about function notation that y equaled f of x for a function, that they were the same. The reason they use this notation here is to tell you before you do anything that you know this thing is going to pass the vertical line test. Okay, so you know it's already a function, which is a good thing to know as we move throughout the rest of this course and into Algebra 2. All right, so anything that is of the form x squared, start with that, x squared, okay, f of x equals x squared or y equals x squared, is called the quadratic parent function. Okay, meaning that it is the simplest version of a quadratic. Okay, and then everything else, every other quadratic function, is based off of that or starts with that. Okay, come down here. It says the graph of a quadratic function is a U-shaped curve called a parabola. Okay, so if we look at this shape down here, okay, it's U-shaped. We call that a parabola. Okay, it says every parabola has two sides or branches that match perfectly. And what I've done here is I try to color coordinate it. We see that the blue side here, or the blue branch, okay, matches perfectly to the red one. Okay, if we were to fold on this y-axis. Okay, so envision having this graph in your hands on a solid piece of paper, and you were able to fold on the y-axis on that solid piece of paper. This blue branch would land directly on top of that red one, or vice versa, the red on the blue. Okay, this property of matching is called symmetry. Okay, your body has symmetry. You know, butterflies have symmetry. A lot of animals have, obviously, most animals have symmetry. But it is something that we see a lot with graphs, and parabolas in general all have some type of symmetry. Okay. In this situation, the line that you would fold on to recognize that symmetry, so that y-axis right there, we call that the axis of symmetry. Okay, and we can write an equation for the y-axis and all that kind of stuff, and we'll do that here in a little bit. So note, if you folded the graph on the y-axis, the right-hand side or the blue side would land on the left-hand side or the red side. Okay, this is called y-axis symmetry. It says the point 0, 0 is called the vertex. Okay, so if we look at this, when we read a graph, we always read it left to right, like we're reading a book. Okay, so I'm going to start on the left-hand side of this graph, and I'm going to read it left to right. So if I'm reading left to right, it actually puts me up here where my cursor is. And as I move to the right, my cursor is going to start to decrease. Okay, the y values are getting smaller and smaller as my cursor moves towards the right. Okay, so we would say that this red graph is decreasing. Okay, at this point right here, where my cursor is right now, to highlight it, we see my blue cursor. Okay, right there is the transition from decreasing to now it's increasing. Okay, so now my graph, my cursor would be going up. My y values are getting bigger and bigger now as I move to the right. So at that point of transition from decreasing to increasing, we have what we call a vertex. Okay, that point right there is our vertex. Okay, it says each parabola has a vertex. Okay, and it's essentially where the graph changes direction. Okay, when we look at any parabola that is of that form, any quadratic equation, okay, if the a value is positive, and that's what this is saying right here, if a is greater than 0, so it's a positive number, so we're looking at that number right there being a positive number, okay, then the vertex is called a minimum because it will look, the graph will look like this, okay, and that point right there will be the lowest y value that we ever get to, okay, so we call that a minimum. Let me just give you we'll get into GeoGebra here real quick to graph one of these. So if I go y equals ax squared plus bx times c. So what this allows me to do, it creates these little sliders that I can change what the equation looks like, and then that will automatically then adjust the graph. But if you look at this, okay, I'm going to ask this thing to find the minimum point. Okay, so let's see here. So that point right there, A. See if we can get the ordered pair here. Okay. So point A is referred to as a minimum because this 0.5 is the smallest y value that you will ever see on this graph. If I put another point on here, let's put that point B. Let me look at this point here and change it to red. That's good. Let's look at B. And let's get its value on there as well. Okay. So now let's compare that number right there, the 6.27, to this 0.5. Obviously, B at 6.27 or 6.82 or 7.42, that y value is bigger than that y value. As I move B, okay, B is always going to be above that red point. See 0.7, that's above 0.5, okay? The only time that it's not going to be above is when it's exactly the same point. So, I think I had it there for a moment. Right there, they're the exact same point. So that 0.5 and that 0.5 are the same y value. But when I go to the right of that, now you see that y value has gotten bigger than this one. So this red point is called a minimum, okay? Because there are no other y values. You can see that using this point B. None of these y values here will ever get smaller than that. So that's the smallest one possible. So we call it a minimum, okay? That happens, look at this a value here that I can change. As long as I keep that a value bigger than 0, Okay, so as long as I make it positive, that number right there is always going to be or that vertex, that point is always going to be the smallest one, or the lowest one on the y-axis, so it's a minimum. Okay, that changes when I make it a negative. Look what happens when I make it a negative. When I make it a negative, now that red point, if I compare that 2.25 now to this 0.61, that 2.25 is bigger than 0.7. It's bigger than the 0.61. It's now bigger, obviously, than any of these negative numbers. Okay, so now that red point is a maximum. Okay, still a vertex, but now a maximum. So what happens? We go back to these notes. When A is positive, you're going to get a graph that looks like this. We say it's opening upward, okay, and that's called being concave up, or sometimes called having upward concavity or something like that. Okay, what I like to think about it is, it looks kind of like a cup. If I was going to pour water in it, okay, pour water in it, it's going to hold that water, okay, and that's when A is bigger than 0. When A is negative, your graph, draw a quick sketch here. When A is negative, your graph is going to look like that, and it's going to be what we say concave down. Now it'd be pouring the water out. Okay, so that's what this bullet here is talking about. When A is negative, when that number right there is a negative, we have a parabola opening downward, and we say it's concave down. Okay, that then turns that point into a maximum. This point here, because it was concave up, remember we called that a minimum. Okay. It says in the following examples, identify the equation of the axis of symmetry, and then determine the vertex, and then determine if it is a maximum or a minimum. Okay, so what we like to do is find what the vertex is. So the vertex is the place where we change directions. Like I said, if I'm looking at my graph reading left to right, right now, if I just start tracing it, right now my y values are getting smaller and smaller and smaller. Okay, so going that way, they get smaller and smaller. Eventually, though, we see there's a change in behavior, and we start now going to the right. We're getting bigger and bigger now. Okay, this was decreasing. This is now increasing. The place that they change is right there. That's called your vertex. Okay, that is your vertex. So that vertex is located at what point? Well, the x value is 3. The y value is 1. That is my vertex. Okay. Now, what is nice about that is that value right there, the 3, is the point that we use, or the coordinate that we use, to identify the axis of symmetry. Okay, we usually make it a dotted line, doesn't matter though. Okay, but that is the line that if we were to fold on that line, this right-hand side will fall exactly on this left-hand side. If you remember how we write the equation of a vertical line, it is always x equals, because we're passing through the x-axis, and then the value that we pass through, so x equals 3. So that's the equation of my axis of symmetry. Okay, got my vertex, and now the question was, is this a maximum or a minimum? Okay, well, if it's concave up, okay, this is a minimum. This is a minimum, and the minimum y value is 1. That's the smallest y value that we'll ever come across. So 3, 1 is my vertex. It's a minimum. The axis of symmetry is x equals 3, and this thing is concave up. Okay, those are all facts that we're kind of interested in as we investigate these parabolas. Okay, so we get to this next one. Okay, so left to right, we're decreasing, 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 decreasing. At this point here, looks like the transition from decreasing to now increasing. So this point here is going to might be my vertex. So it's an x value of -2. Looks like a y value of -4. So what that means is that this is, because it's concave up again, concave up, Okay, that means this point here is a minimum. Okay, and our axis of symmetry would be this line right here. If I fold on that line, axis of symmetry is always going to pass. It's always a vertical line that is going to pass through your vertex. Okay, the equation of my axis of symmetry here is x equals -2. And we'll come over here to this one. This one's a little bit different. This one now changes direction. Okay, so instead of being concave up, this one here is concave down. So if we were able to see what the equation was for this, your a value would have been a negative number. Okay, so it'd be ax squared. That a is going to be negative. So maybe it's negative, like in this case, it's probably like -1/2 x squared and -1/3 x squared or something like that. But if we look at this, we're increasing. It looks like about right there. We changed to decreasing. So I'm going to say that is my vertex, which is the point 2, 3. Okay. Now, because this is concave down, remember this is the largest y. That 3 is the largest y value you ever come across on this graph. So this is a maximum. We still have an axis of symmetry that passes through the vertex, and that is going to be the line x equals 2. Okay, so you're going to see a handful of questions that ask you to kind of do that. Okay, look at a graph, determine vertex, determine axis of symmetry. When we start graphing these things on our own, those are the first two things you're going to do. You're going to find the vertex, you're going to identify it through the equation, you're going to draw in your axis of symmetry, and that's going to help you graph the overall parabola. And that happens in section 9.2. We start doing that. Here it says graphing y equals ax squared. Okay, so we'll graph a couple of these using some kind of basic concepts that we've already learned when we graph lines. So let's first identify the vertex. Okay, so any quadratic with this form will have a vertex located at 0, 0. Okay, so there's no other like bx or c that is attached to this. So you're only going to see like 2x squared or 1/3 x squared. There's no plus or minus anything else beyond that x squared term. Okay, so anything of this form, okay, is going to have a vertex located at 0, 0. Okay, so that's nice. Second, it says choose a convenient x value that works well with your coefficient and evaluate to find y. Okay, we'll talk about that here in a moment, how we do that. For instance, here, I probably would not use x to be 1. Okay, because if I put 1 in here, I'm going to get 1 times 1/3 is 1/3. I don't want to graph 1/3 on my y-axis. If I plugged in 2, I would get 4/3 here. I don't want to graph 4/3. Okay, so we'll talk about what it means to be a convenient x value. Okay, we did the same thing with lines, if you can remember back that far. Third says use the y-axis as the line of symmetry to find points on the other side of the parabola. It says graphing a parabola. When graphing a parabola, it is imperative that you use at least 3 points, in which one point is the vertex, and the other 2 points are on opposite sides of the vertex. This will guarantee that you create a complete image of the parabola. Okay, it says it is customary to usually use more than 3 points as well. Okay, so what I want to make sure we understand here is that when I want to graph, let's just say, I'm going to start with y equals x squared. I know that if I go y equals x squared, I know 0, 0 is going to be on there. I know 1, 1 is going to be on there. And I know 2, 4 is going to be on there. If those are the only points that I graph and I connect them with a smooth curve, this is what you would see, x squared when x is greater than 0. That's what you would see, okay? But that's not the graph we're looking for when I graph x squared. I'm looking for that thing. So what it makes sense to do is instead of graphing that c value at 2, 4, maybe it makes more sense to go -1, 1 and use dA and b and use a smooth curve, and now you get both sides of that parabola to the right of A and to the left of A. Okay, but if you only use, obviously, these 3 points, you would not get this left-hand side or know that left-hand side exists that way. So here we go with 2x squared. So when this number here is a whole number, to be honest with you, I don't really care the x value that I use. Okay, so obviously we know if x is 0, plug that in here, you get x squared, which would be 0. 2 times 0 then would be 0. So we get 0, 0. So that's what that first bullet said, is that in this form, you're always going to have the point 0, 0. Okay, so that's nice. So I plot 0, 0. Okay, now if I try 1, okay, plug 1 in, square it, I get 1 again, multiply 1 by 2, and I get 2. So again, remember I'm using order of operations here, so I really have this, and if I want to evaluate that, order of operations says you got to do that first, so 1 squared is 1. And that'll leave you 2 times 1, which then gives me the 2. So I plot the point 1, 2. Okay, so here's the nice thing. Because I know that that's the vertex, okay, and because I know that my axis of symmetry passes through the vertex, okay, we should know that this point right here, which is at 1, 2, when I fold on this pink dotted line, this point 1, 2 is going to reflect over here to negative 1, 2. Okay? And just to check that that makes sense, let's see if I evaluate at negative 1. So I get 2 times negative 1 squared. Well, negative 1 times negative 1 is 1, so I have 2 times 1, and that gives me 2 again. So at negative 1, I have a y value of 2. Okay? Try another one. Let's plug 2 in here. So if I use an x value of 2, you would have 2 times 2 squared. So 2 squared is 4, so I have 2 times 4, which just gives me 8. So 2, 8 would be another point. Okay. Now, likewise, if I were to fold on the pink axis of symmetry, this point is going to lay over here to right there, which is negative 2, 8. Okay, and if I tried negative 2, you can verify this. Go 2 times negative 2 squared. Well, negative 2 times negative 2 is 4 again, so now I have 2 times 4, which is still going to give me the same 8 right there. Once you have that, and it's kind of hard for me with the tablet that I use to draw the parabolas, but you would connect with a smooth curve. Okay, and the idea is that you have at least 3 of these points, preferably having the vertex 0, 0, being one of your 3 points, and then one of these 2, and then one of these 2. Okay. Usually, if you're going to use one of these 2, you use that one. Usually, you have that one on that side. If you use 2, 8 as the point over here on the right, then usually you have negative 2, 8 as the one on the left, just because the axis symmetry allows you to find that one a lot easier. The next one, using 1/3 x squared. Okay, this is where I think it's important to use a convenient value of for x. Okay, and the idea here is because we got a fraction, I'm going to try to choose my x value so that there are multiples of that number right there. Okay, you'll see the benefit of that here in a moment. So I know I'm going to choose 0. If x is 0, y is 0, so that's my vertex. Okay. So now I'm going to use multiples of 1/3, and you're going to see the reason for this. If x is 3, okay, or I guess not multiples of 1/3, but multiples of the denominator of 3. If x is 3, I'd have 1/3, and then my 3 squared. Okay, well, order of operations says you got to do that first. That gives me 9. So I have 1/3 times 9, and 1/3 of 9 is 3. So it gives me 3, 3. Using a multiple of 3 as my x value guarantees that this y value is going to be a whole number. Okay, if I would just arbitrarily say, oh, I want x equal 2, then I would have 1/3 of 2 squared. 2 squared is 4, so 1/3 times 4 is 4/3, or 1.3 repeating, which is fine. It's true. That's an ordered pair. 2, 4/3 is an ordered pair, but graphing 2, 4/3 be about right there. I had to guess where 4/3 is. 3, 3, I don't have to guess where either of those points are. Okay, so that's the benefit of using a multiple of that. So now the next multiple of 3 would be 6. So I'll try 6. So I'll go 1/3 6 squared. Okay, so 1/3 6 squared is 36. A third of 36 is what, 12? Okay, so 6 comma 12 will be another point. Okay, so 6, and then I run out of room here on my graph, but maybe 12 up there. So there's 11, there's 12. Okay, do that. Do these points in red so we can see them a little better. So 6 comma 12. This here was 3, 3. Like I said, you can have this one, but it doesn't make a whole lot of sense. That was 2 comma 4/3. Okay, and this was my vertex 0, 0. Okay, now if I just put those points on there, I don't get my full parabola. Okay, so obviously plotting those, connecting with a smooth curve. Okay, I just get that branch. But because we know that the axis of symmetry passes through the vertex, okay, if we were to fold on that blue dotted line, this point here at 2 4/3 is going to go to -2 4/3. This point here at -3 3 is going to go to -3 +3, and this will go from 6/12 to -6/12. And now if I do that and connect that with a smooth curve, now with the blue and the red, you get the full parabola. Okay, so that's kind of the structure that we're going to use in graphing these things. All right. Questions that they often ask is, can you list the domain for all the functions that we deal with? Okay. Remember, the domain is the x values. Okay, so all the x values that we can have. So I guess the domain is a way, listing the domain and range is a way to provide the infinite order of pairs on a graph. Okay, or a way of identifying what all the possible x values could be for all the ordered pairs and all the possible y values for all the ordered pairs. Okay, so range is the y values. Okay, so domain is the x values, range is the y values. So the common practice to determine the domain and range values for quadratic functions. Okay, so the domain, so these are the numbers that you're able to input into the rule. So if I have like a rule like y equals x squared plus 5x plus 6 or something like that, or maybe we just go back to one of the top ones like y equals 2x squared. That was the first one we did here, right there. If I just use that, okay, the question is, what x values are you allowed to put in here? Well, I'm allowed to put in anything as long as it gives me an output, as long as it gives me a number back. So if I choose like 0, when I plug 0 in here, I get 0 back. When I plug in 1, okay, what do we get when we plugged in 1? We got 2 back. When I plugged in -1, I got 2 back. When I plugged in 2, I got 8 back. No matter what you think about plugging in there, you can evaluate and get a number back. You can get an output, okay? So the domain in this situation is any x value that you could possibly think of, because each one of them will allow you to get an output back. Okay, it says generally in algebra there are 2 common instances when there are values you cannot use. Okay, and that is when there's division. We have no division here. Okay, division, the problem that occurs is that when you divide by 0. Okay, so we don't have that here, so there's no worry there. The other issue is when you have even roots, so a square root or a 4th root or something like that in your equation or your function, and we don't have any of those here. Okay, you can't take square roots of negative numbers, and we'll get into that in the next chapter. Okay, so because a quadratics, I should say because all quadratics should say have neither of these issues, the domain of every or any quadratic equation is always stated as all real numbers. Okay, so there's a couple ways that you'll see this written. So domain, I think on Math Excel there's going to be like an option for domain, and one of the bubbles will say all reals or all real numbers, something like that. And you'll just click that bubble, okay? Other places, let's say you're on the ACT, you're on in a different course or something like that, you might use what we call interval notation. And basically what you say for all real numbers is that it's the numbers from negative infinity to positive infinity, okay? And the final way is that the set of real numbers has a symbol attached to them, okay? And it's you use a double bar here, and then you turn it into an R, okay? And that stands for that phrase, all real numbers, okay? Those are 3 different ways you can see it. Like I said, for the most part in this class, all real numbers is going to be written out for us. These are things that you'll see maybe stated in other courses, but they don't describe what, they just start using that notation, never really explain what the meaning of it is, okay? The range, okay, the range is not as easy to figure out, okay? But it is the y values. It's the output values that you get when you choose those input values, okay? So algebraically, these are not always the easiest thing to find. However, with a graph, it's a simple process, and I'll walk you through that process here in a moment, okay? So here it says graph y equals negative 2x squared, determine the vertex, is it a max or min, find the axis of symmetry, determine the domain and range. So these are all things that we're interested in when we construct a parabola. So it's of the form ax squared, so I know the vertex is going to be 0, 0. If I plug in x to be 0, 0 squared is 0 times negative 2 is 0, so 0, 0, okay? Now if I try x to be, let's say, I'll just say 2 here. Actually, let's not go 2 because I ran out of room. Now let's go 1. If x is 1, so I have negative 2 times 1 squared. So 1 squared is 1 times negative 2 is negative 2. So 1, negative 2. Okay. Now remember, so I'm going to stop there with my chart here. If you want to put more points in with your chart, go ahead. I would suggest, since you've already got an x value to the right of that point, you know that's your vertex. I think it makes sense to don't continue to put, if you can, but you might be wasting your time. I would not go to 2 because I've already got a point to the right here of the vertex. I would want to try to find a point to the left there, so maybe it makes sense to go negative 1. But if this is my vertex, I know my axis of symmetry passes through there, just like that. So this point here at 1, negative 2 will be symmetric, or maybe even say reflective to that point there at negative 1, negative 2. And if you try that, if I go negative 2, negative 1 squared, do my algebra, that gives me 1. Negative 2 times 1 is negative 2. Okay, so these 3 points are enough to give me a good sketch of my graph. Okay, so now I know that that's my vertex at 0, 0. Okay, if I think of this as concave down, so that point right there, that vertex, is the largest y value that I'll get. If I look at all the other y values on here, they're all negative. That one is 0. Okay, so 0 is bigger than any negative number I can ever think of. So that max, or that vertex, is a maximum. My axis of symmetry is the y-axis, and that's the equation x equals 0. Okay, this is concave down, and now it asks me the domain and range. Okay, so when I do the domain, I'm just going to say D for domain. I'll put a colon here, and I'm going to say either in words, all real numbers. Okay, or if you want to, you can write that. Okay, my range is a little bit different. When the range is being asked from your graph, what you do is you're going to take a horizontal line, you're going to put it all the way at the bottom of your graph. Okay, and you're going to envision that as you take that horizontal line and start sliding it vertically, okay, you're going to record the y values that horizontal line touches. Okay, so what I want you guys to understand here is that this is going down forever in that direction. So the first y value that this would interact with would actually be negative infinity. Okay, it's going to come up and keep going, so eventually I get to like negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0. If I go above that, it doesn't intersect any of the y values on my graph here. Okay, so it looks like y being 0 was my largest y value. Okay, so when I talk about my range, and I'm kind of getting a little ahead of you writing it this way. Let's say that my range were y values that were all less than or equal to 0. Okay, so in this form, just kind of think about maybe a shortcut here. If it's this form and it's concave down, your range is going to be that always. Okay, so if this was, no matter what that number right there was, -2, -1, -3, -1/3, -1/2, whatever, as long as it's negative, this is going to be your range. Okay. Let's do this one. It says graphing y equals. It's changing the rule a little bit. Okay. So these were all, everything we've done so far was just, you just had the x squared component. Now I'm going to add a constant to the end. Okay, some plus c. So this series of graphs is similar to those of y equals ax squared. Okay. This should say the, I got a lot of typos in this. The y-axis is still the axis of symmetry. It says, however, the graph is shifted c units vertically. It's up if it's plus, and it's down if it's minus. All right, and so therefore, in this situation, the vertex will always be located at 0, c. All right, so let's just kind of look at this relationship here. What I'm going to do, I don't want to graph it. Well, I'll do it this way. Let's go to this here. So I've got a graph y equals x squared. So that's the parent function. Now I'm going to go write y equals x squared plus some c. Okay, and I'll create a slider for c. And what I want to do is make that c increase by 1. Okay, so right now we see that these two equations are identical. Okay, so the graph is the same. Let me change this one to red. All right, so you see that they're the same. So the black one and the red one lay on top of each other. Okay, when I make that c go to plus 1, now you've seen that every single point on here has been moved up 1 unit. If I put on some points here, let's put let's say we go 1 comma f of 1. Just kind of bear with me. I know the notation might not make sense to you right off the bat here, but what that does is allows me to show you that point right there, okay, which was on the x squared, and now I'm going to type in 1 comma g of 1, which is now going to put that point there. Okay, and what you see here is that when I do that, you can see that that point was simply moved from x squared. That point, because of this plus 1 right there, just got moved up 1 unit. Okay, let me show you. Let's go f of, so let's go x being 2 and then f of 2. So it gives me that point c. Okay, so that's a point on the parent function. So it'd be 2 comma 4. Let's look at 2 comma g of 2. It puts that d here, which is on the red one. But if I look at those, you see how they're only differing by 1. That d is 1 unit up from c because of that plus 1. Now if I make this a plus 2, you see that that a was still at a y value of 1 here. The b is now at a y value of 3. Well, the difference between 1 and 3 is that 2 right there. Look at this c. It's a y value of 4. D has a y value of 6. Well, the difference in that is that 2 right there. So what's happening here is that every single point that is on the black curve gets moved up that C unit. So let me do this here real quick. Let's put that right there. Okay. Now this is geometrically, it's called a vector. But let's just make it blue real quick. All right, and then this number right here is going to tell you the length of that vector. And basically what it's doing is just showing you that it got that point A moves up 2 units to become that red point B. If it was a +3, you see that that distance there is 3 units. If it was 4, you see it gets moved up 4 units. Okay, so we could do this everywhere. 0, 0 would be a point here on this parent function. 0, 4 is on this one. Well, that distance there would be 4. So I should be able to take, let's just do this. Let's put a point that I can move here. And let's make a vector. The vector, I think it's vector start point. Let's just say it's going to be the x value of E. And then, okay, do it this way. Hold on a second. I don't think I can do it that way. There we go. All right, so let's take this orange vector, which is showing me a length of 4. No matter where I move E to, you see that it matches up E prime. And that distance right there, that is always 4 units. I click on that, E to E prime, you see it tells me 4 units. If I were to make it like -5, you see now the red graph goes down. So it takes the black one and moves it down. So it went down 5, so it moved E 5 units down everywhere. It moves it down 5 units everywhere. Okay, so that's what these numbers at the end are going to do to your graph. They're going to move them up or down. Okay, so if they ask me, okay, look at y equals x squared plus 3, and they ask you, well, where's the vertex? Well, we can do one of two things. We can say, okay, well, let's plug in x to be 0. If x is 0, that goes away. 0 plus 3 then is 3, so the y value is 3. So 0, 3 is my vertex, okay? Or I can remember that it's of this form here that is explained. It's ax squared plus c form, and this rule here says that your vertex is always at 0, c. 0, this 3 is my c, so 0, 3. Okay, now if I try 1, so let's say x is 1, so I have 1 squared, which is 1, plus 3 is 4, so 1, comma 4 ends up being my ordered pair. Okay, remember this was your vertex. Okay, your a value is positive, so this thing's going to be concave up. Okay, and now we can use symmetry. We know that this is my x-axis. Not my x. That's my axis of symmetry, which is the y-axis. It's the equation x equals 0. So then with symmetry, that distance right there will be copied to there. And now you've got enough to make that portion of your graph. Okay, concave up, vertex 0, 3. Okay, let's talk about the domain. Domain, all real numbers. That's a given, always going to happen. Okay, the range, let's think about this. What's the first y value that that horizontal line comes in contact with? The first y value that it comes in contact with is 3. So my range starts at 3, y values that are starting at 3, and then we see that we also have y values that are bigger than 3. So we're looking at y is greater than or equal to any value bigger than or equal to 3. All right, so in your homework, there's a couple questions that talk about falling objects. So I just want to kind of give you a brief rundown of what a falling object looks like. And this is a physics model that I made that can, we're not going to get into the whole load of information that's here. But basically what I want to show you here is that whenever you take a object, okay, and you kick it, throw it, launch it, whatever, it's going to, you kick it through the air, launch it through the air as a projectile, it is always going to be tracing out a parabolic arch. Okay, if you're into archery, or if I know some of you are hunters, when you shoot an arrow or you shoot a bullet, that object, even though it's moving very fast, okay, it is still tracing out a parabolic arc. Okay, so this is demonstrating that. So I want to do something here where, let's say I have so right here, so my x-axis represents the ground over here in the yellow. So let's see if we can make my x-axis a little bit darker. Okay, so this is the ground. Whenever you take an object and you launch it, kick it, throw it, whatever, it's going to take a course or a path that is parabolic. Okay, so we're kind of seeing right here, and I'll make it a little bit more drastic here. Reset. Let's go to. So right here, I'm setting initial velocity, meaning that I'm going to maybe, let's say I'm throwing a baseball and I throw it 60 miles an hour. Okay, so that's my initial velocity. If I throw it, okay, and that's a little bit crazy. Let's do this. Let's go down to, let's say I throw it 30 miles per hour. There we go, it's a little bit better. You can see the path here, this dotted line that my ball or projectile would take. Okay, now this is saying that I would have thrown it at 30 miles per hour at an angle of 18 degrees, means it's going to land 52 feet away from me, 53 feet away from me, or meters away from me in this case. Okay, but it takes a parabola. Okay, what this is showing over here is actually the height of that parabola against time. So this here is a horizontal displacement versus a vertical displacement. So this is showing me that when I threw it, it reached a height of almost 5 meters as the maximum, and it landed about 54 meters away from me. This here is showing at a certain time how high off the ground the ball was. Okay, so one of the things that our textbook gets into is asking this: if you launch this thing straight in the air, you shot it straight up. Okay, so think about doing this. Take a ball and just throw it straight above your head and let it come straight back down. What you would see is the ball going straight up. It's going to reach its maximum, and then it's going to fall straight back down. Okay. Now that's not very interesting when we're talking about displacement, how far it's moved left and right from where I threw it. But over here, you see it's a little bit different, okay? Because the x-axis is not a distance anymore. The x-axis is in terms of time, and it's in seconds, okay? So what we're saying here is if I throw this ball straight up, okay, after, get about right there at 2.92 seconds, okay, we reach a little bit more than 45 meters, okay, and it's going to be the highest that the ball reaches. After that, if I continue, the ball starts to fall, okay, so at 3.98 seconds, the ball is about maybe 41, 42 meters, Okay. Gonna finish this off. Okay, and we're seeing here at about 6.14 seconds, the ball gets down to a height of 0. So this here is a height axis or a vertical distance axis, and this is time. Okay, so this is showing that after about, I think it was like 2.5 seconds, something like that, 3 seconds, that we reached a maximum, and then down here at a little bit after 5 seconds we hit, or 6 seconds, we hit the ground. What your homework is going to ask you is a question like this. So we can adjust this. We can take, and I can lift the ball over here off the ground. And the idea is now maybe I'm standing on a building or a cliff or something like that, and I'm going to launch this ball. Okay. So if we go back to that first scenario I gave you, and we have like a launch angle like this, the idea is I'm going to fire this, and we take that parabola, and this is the vertical and horizontal displacement. Okay. The idea with what your homework does, it says you have an initial velocity of 0. So what does that mean? It means maybe I'm standing on top of this building, and I'm just going to drop the ball. And you can see what this over here would look like if I was to do that. If I was standing, open my window, whatever, and drop this ball out of the window, it's going to go straight down. Okay? But what happens physically is that because of the acceleration of gravity, the longer this thing is in the air, the more acceleration it's picking up, the faster it's going to go. So after 1 second, it's only falling at what we call 32 feet per second. But after 2 seconds, it's going 64 feet per second. So it's picking up speed as it's falling. So you can kind of visualize that. You can see that happening here. This ball starts off not moving very fast, but towards about right here, you can see it visually gains speed, and it's moving a little bit quicker now. Okay. What your textbook is asking, and I'm going to zoom in on this so you can see it a little bit better, is say, okay, if we're going to start at a height of 22 meters. Okay, so that's how tall my building is. 20. Let's put it down to 20. 20 meters. And then the question is, okay, well, what does that look like in regards to time? How, if we were to plot these points, what does this graph look like here? Okay, so at 0 seconds, my ball is at a height of 20 meters. Okay, after 2 seconds, or 1.94 seconds, you can see your ball is about 1.9 meters. Okay, so if we think about this, this is parabolic. Okay, but every one of these red points that I'm showing you over here is a time. Each one of these dots over here is a time, comma, a height. Okay, time, comma, a height. But if we were to look at the rule that is being created here, if I can find where it went, we'll do it this way. So if I type in here, let's go y equals negative 4.9 x squared plus 20. Okay, there's a parabola. Okay, and hopefully you can see here that red dot is going to follow that parabola. Okay, so the parabola I typed in here was something that looked of this form. Okay, so I'm going to kind of walk you through this example. It says an acorn drops from a tree branch 20 feet above the ground. The function h equals negative 16t squared plus t models, or gives the height of an object after t seconds. They should actually write this h of t equals negative 16t squared plus 20. It says, what is the graph of this quadratic function, and about what time does the acorn hit the ground? Well, let's just do a couple things here. One, we know that this thing is of the form a x squared plus c. Instead of using x, using t for time, but it doesn't matter. remember, everything of that has a vertex at 0, comma c. So the vertex of this thing is going to be at 0, comma 20. This number here is my A, and it's negative, so that means this thing's going to be concave down. All right. And there's another thing that we're interested in here, and this is time. So this is the x-axis, it's my t value, my time. We're only ever interested in time being a positive number, so we don't really worry about the left-hand side of this parabola. But this point here is 0, comma 20, okay? And my parabola is going to go that direction. It's going to go concave down. We know this is a max, okay? Now the question is, when does this thing hit the ground? Well, what would the y value be right there when it hits the ground? The y value would be 0. Y equals 0. Okay? Well, the y value is the h of t. Okay? It's the height. Okay? So it's this number right here. If I plug in 0 there, equals negative 16 t squared plus 20, we should be able to solve this equation. I'm going to subtract 20 from both sides. I'm going to divide both sides by negative 16. Okay, so now those both reduce. They both have a 4 in them. So I get 5/4 equals t squared. So a square root, I get radical 5 over 2 is equal to t. Okay, now you can use Desmos or whatever you want to evaluate that. Let's get Desmos up real quick. If I go square root of 5 divided by 2, it gives me that number right there. And that's a time, that's in seconds. So that's how many seconds it takes for this thing to hit the ground. And we can check that. If I say, I'm going to let that be t, type in negative 16 t squared plus 20, does it give me 0? It gives me, if you think about that, that's pretty close to 0, scientific notation. But even if you do this, so negative 16 t squared would be negative 20, so if you can visualize adding 20 to that, it would give you 0. So that a couple questions towards the end of your homework assignment will involve something like this, asking you to find that t. So we take a square root, you get two answers, you get positive and negative. The reason we're not worried about this negative one, because I could do negative, okay, and you still see when I plug that in here to negative 16 t squared, still gives me negative 20 here. So adding 20 to that still gives me 0, but that's a time, and we don't worry about time ever being negative. So that's why we get rid of the negative answer when we take the positive.